So here's a little bit of help for 1.8. Number 4, we drop a wrench from the top of a mast on a sailboat. Will the wrench hit at the same place on the deck? Whether the sailboat is at rest or moving with a constant velocity. What you have to understand is, here's our boat, okay? If I drop the wrench and it's not moving, nothing's moving, it lands straight below. If, however, I give velocity to the boat, okay, or the ship, that means that the wrench, if you think about this moving through time, the wrench is also moving with the same velocity through time. And so while the wrench now has a horizontal velocity as well as the drop, it's going to move and drop like this. But the boat will have moved to a new position in that same amount of time, and it will end up landing at the same place at the base of the mast where it was before. So question number 5 talks about very similar. If we drop a stone and we throw a stone horizontally, in other words, if one's doing this and the other's just being dropped straight down, certain things are going to happen. Vertical displacement, they're both going to go the same distance vertically. Horizontally, the one that's shot to the right is obviously going to cover more distance. But will they hit the ground at the same time? The answer is yeah, absolutely. Because we know the horizontal and vertical are independent from each other. Okay, that takes us to question, 6. Yeah, projectiles launched at ground level with an initial speed of 50 meters per second and an angle of 30 degrees above the horizontal. It strikes a target above the ground. So here's the ground. There's our initial launch of 30 degrees, 50 meters per second. And it's going to come out here like a projectile, and it's going to hit some target 3 seconds later. So t equals 3 seconds. And we want to know what are the x and y distances where the projectile was launched to where it lands. Now, that would be delta x. So there's my delta x movement, and there's my delta y movement. That does not mean that this 30-degree angle is a part of this, because we notice it's probably going to come up above and then land below, or be on its way up. It's not a right triangle in terms of its position change, but we do want to know delta x and delta y at 3 seconds. So we do know that there is a v naught in the y direction and a v naught in the x direction that are going to be important for us to be able to solve these. So when we look at our x and y pieces, the v naught in the x direction, it's how fast is this moving side to side. We know vx we can't use because ax is 0. Delta x is what we're looking for, and the time we're given is 3 seconds. So if we can find v naught x, then we should be able to find delta x. We're not even going to worry about y right now. To find v naught x, we're going to have to use our calculator, and using a right triangle from the launch point, we know that it's the hypotenuse times the cosine of the angle. So 50 times the cosine of 30, I'll grab my calculator here real quick. So 50 cosine of 30, enter 43.3. Let's just real quick check. Yeah, we're in degrees. So 43.3 meters per second. And when we times that by 3, because it's 3 seconds, remember we're going to be using delta x equals v naught t. So that's our initial velocity, 43.3, times our time. So we times that by 3. Oh, whoops. I got too many times in there. All right, times 3. We get 129.9. We're going to have to round that. My delta x is going to come out to 130 meters. Now, I think the note sheet or the textbook on OneNote says 1.30 times 10 to the second. That's scientific notation for 130. So don't let yourself get bothered by that. So we figured out what x movement there was, 130 meters. In the y, we're still going to need v naught y. Vy would be how fast is it moving when it hits the target. I don't think that's asked for, and we're probably not going to mess with it. We do know ay is 9.8. Now, I'm going to make that a negative 9.8 because I know the initial velocity is upward, and so that's going to be counterintuitive or counterproductive. So we've got to have both of those. Delta y is what we're after, and again we know that t is 3 seconds. So if we can figure out what v naught y is, we can go through the same process there. V naught y would be 50, the hypotenuse, times the sine of 30. Now the sine of 30, for those of you who are real comfortable with your trig and your right triangle trig, that's half. So this turns out to just be 25 meters per second. We're going to have 25 meters per second. You put that in the calculator if you want to calculate it yourself, but I think I'm going to go through equation number 2 in terms of our kinematics. Let's open this up a little bit. That tells me that delta y equals v naught, 25, times t, that's 3, plus 1/2, negative 9.8. That's really important. We have that sign change there, times t squared, which would be 3 squared. This is something that we can throw in the calculator from left to right, and we should be able to just get that delta y is 30.9 meters. Okay. All right. Let's look forward at a couple more questions before we're done for helping out a little bit here. 7 will be very similar. It asks for a lot of individual pieces, but it does start at a horizontal launch. That should tell you that v naught in the y direction is 0. Okay, but it's going to ask you for all this fill-in, and at the end you are going to need to know the horizontal and the vertical velocity. But remember that the horizontal velocity never changes. So if you know the initial horizontal velocity, you'll know the final horizontal velocity. Number 9, arrow shot at a height of 1.5 meters toward a cliff H. It's shot with 30 meters per second at 60 degrees above horizontal. It lands at the top edge of the cliff 4 seconds later. Okay, what is the height of the cliff? And then was the maximum height reached by the arrow in its trajectory? What is the arrow's impact speed just before hitting the cliff? So this has quite a few different things in it. The fundamental thing you're going to have to work with, obviously first, if you're using a 60-degree angle and it's being shot at 30 meters per second, first thing that you're going to have to do is find v naught in the y direction and v naught in the x direction. That's fundamental, based on the same thing we did last time. Find those values. A couple of other things you're going to need to know. If we're shooting it at 1.5 meters high off the ground, that's essentially how tall I am when I hold my bow and arrow and shoot the arrow. Whatever height you get whatever delta y you get when t is equal to 4 seconds, this delta y number has to include or add to it 1.5 more meters if you want to know what's the height of the cliff. So if I get 30 meters for delta y, it would be 31.5 meters for the height of the cliff. The next thing you'd look at is, hey, how high is its highest point? At its highest point, okay, what we're going to want to do is set Vy to 0, and we won't know the time. So you're going to have to go through, and this is really 3 separate problems, and you should look at each of them individually, not try to keep using the same information. Do one, and then do the next, and then reassess every time each of these questions. I do want to look at question number 13 with you, and then I think we'll look at 15. So if we look real quick at number 13, we've got, again, we're just trying to give you a little bit of help, a little structure to support you with it. It says a tennis ball is struck such that it leaves the racket horizontally, there's the ball, horizontally with a velocity or speed of 28 meters per second. The ball hits the court at a horizontal distance, delta x of, what are we at, 19.6 meters. And what is the height of the tennis ball when it leaves the racket? We're looking for delta y. Well, if we go in and do our x and y information, we can fill a few of these things in. For instance, v naught in the x direction is 28. meters per second squared, or meters per second rather. Vx we never use. Ax of course is 0. Delta x is 19.6 and t is unknown. But if I use delta x equals v naught t, then all I have to do for t is take my delta x and divide it by v naught, right? If that's how you would solve that over. So 19.6 divided by 28, 19.6 divided by 28 produces a 0.7 second time. That tells me how long it takes for the ball to drop. That matters because it helps me figure out the information over here. V naught in the y direction. If the ball is launched horizontally initially, that means we have no vertical displacement or vertical velocity to begin with. Vy I don't know and I'm not sure that I need it. Ay is 9.8 meters per second squared. And because I'm going to talk about this measurement as a positive, my height drop, I can use a positive here and it shouldn't matter. Delta y, that's what I'm after. And then t, we just learned, is 0.7. So if I'm going to use this information, I can go into my second kinematic. We use this one a lot. Delta y equals v naught, which is 0, times t, which is 0.7. We know that that's all 0, plus 1/2 of our 9.8 times our t 0.7 squared. We should be able to calculate that, just throwing that in the calculator, and come out with the height of the ball being 2.4 meters. So 2.40 meters would be the height change or drop of the ball while it's hit. Okay, last one I want to look at with you is number 15. Again, one of these problems where maybe it feels like there's a lot going on. Let me shrink that back down. Okay, so number 15, we have the 1994 Winter Olympics aerial competition in skiing. In this event, skiers speed down a ramp, slopes sharply upward at the end. You guys have seen this if you've watched the Olympics. The sharp upward slope launches them into the air where they perform aerobatic maneuvers. In the women's competition, the end of a typical launch ramp is 63 degrees above the horizontal. You can imagine, here's the ramp, and this launch angle is going to be a 63-degree angle above launch, above the horizontal. With this launch angle, a skier attains a height of 13 meters. Okay, from here, we're going to end up at our high point of being 13 meters above the height of the top of the ramp. And the question is, well, how fast is the skier's launch speed? We're being asked for V naught. Now, one thing we're going to have to understand up front, okay, we do have a delta y of 13. We know that at the high point, v in the y direction should be 0, because we're going to cap our upward movement right there. There will be no vertical speed at that top of our projectile path. Okay, so there's a couple things we do know. We know our delta y is a gain of 13. We know vy has to be 0 there. What we're really going to find initially is v naught in the y direction. If I can find v naught in the y direction, I should be able to use the right triangle trig over here to just be able to find v naught. I don't think I have to find any of the x information. I don't even know that I need to know how long I'm in the air. Let's look at just our y information and see what we have. V naught in the y direction is our unknown. That's what we're after, because that'll help us go to the original triangle. Vy, based on stopping at the high point, would be 0. Acceleration, of course, is going to be negative 9.8 meters per second squared. Now, I want to use a negative there because I expect this velocity, this initial velocity, to be positive and upward. Delta y, we're told we're going to gain 13 meters, so those have to be different, negatives and positive. And then time I don't know, but I'm going to claim that the second kinematic, or third kinematic rather, should solve this problem out, giving me v squared equals v naught squared plus 2a delta y in this problem instead of delta x. We know that this will be 0 equals v naught squared plus 2 times a negative 9.8 times 13. So I'm going to take some quick calculation of all this. If we take 2 times negative 9.8 times 13, we get negative 254.8. Now I know I'm going to have to move that, right? I'm going to have to move that over by addition, and then I'm going to have to square root whatever that number comes out to be. So bear with me, I'm going to shorthand that a little bit. So I'm going to take the square root of the negative of that number, and the calculator is going to spit out 15.96. I'm going to keep a couple of extra digits just because I know I'm already rounding, and I don't like to round too early. But V naught in the y direction is 15.96, and then whatever else is there. Okay, that is the vertical component of my velocity, my initial velocity, 15.96 meters per second. Using this right triangle, which I'll redraw here, I know I have a 63-degree angle. I know I have 15.96 meters per second, and I want to know V naught, which is the hypotenuse. If I've got the opposite side and I'm working on the hypotenuse, that should lead me to using a sine function. So sine of 63 degrees would equal the opposite, 15.96. And again, I've got that number in the calculator. I'm probably going to use it rather than the rounded version over the hypotenuse V naught. Now, if you've been in my classes before and you've been through the trigonometry with me, we have a name for when we switch these two places and get V naught equals 15.96 over the sine of 63. Those of you who haven't been in my class, we call it the old Welch rule, but it's one that we're going to use relatively often in this class and in other trig-based classes. If I go to my calculator and we do 15.96, well, you know what? Let's go up and grab that number and divide it by the sine of 63. We get 17.92. We're going to have to round that off to 17.9 meters per second. And hopefully that's the same answer we got on there. And they rounded out to 18. But that's kind of how we work through those. It's all about breaking things into vertical and horizontal, and then working with those kinematic equations. Good luck. We'll see you in class.